Hey, Year 12s, thanks for coming. It's good to see you guys. I've still only got 2 people waiting, so it's taken a bit of time for people to find it. I could probably share the link. I'm not entirely sure how to do that, actually. Hang on a sec. Can share, copy. It's taken a bit of time for people to find it. I'm just going to lob that on the chat so everyone knows where it is. There we go. Cool. Right. Okay, guys. I'm going to go straight into electronic configuration part 2. So I'm going to share my screen, get rid of my horrible face. Let's get rid of that guy. I've popped out the chat window so I can still see the chat. If everyone can say a quick hi so I know that they're there, that would be grand. Right. Okay, guys. So I sent you guys a quick homework on electronic configuration. I'm actually, since I know that 4 of you have now done it, so in that case, what I'm going to do is I'm actually going to go through it, and then those people who haven't done it, you guys can have a go. Okay, so let's run through this. So we've got carbon. So you'll be able to mark your own here, guys. So carbon, element number 6, has got 6 electrons. Going to shrink my pen. There we go. 6 electrons. Configuration, full configuration, 1s2, 2s2, 2p2. There we go. The short form will be helium, and it'll then become 2s2, 2p2. There's the short form. Oxygen, it's got 8 electrons, 1s2, 2s2, 2p4. Yeah, if anybody's wondering how I'm doing this, by the way, I'm just going to quickly go to, one of the things I'm going to do is I'm just going to quickly turn off my camera because it means that my laptop runs a little bit more smoothly. So just quickly to show you this, guys, I'm actually just reading the table in my head. So to do lithium was first. We know that hydrogen and helium are in the wrong place. Hydrogen should be there, helium should be there. They're in the 1s block. Yeah, we know this is the s block, the d block, the p block, and the f block. Yeah, so we go 1s2 for those guys, and then lithium we're into. I really want to make my pen a bit thinner. There we go. There we go. And this is the 2s. This is the s block. So this becomes 2s for lithium, 2s1. There's lithiums, but then if you want carbons, you go across and you get 2s2, and then we enter the 2p because this is the second row, and it's the p block, and then it's 2p2. Yeah, and then we went to oxygen. Well, oxygen's the same, 2s2, 2p, 1, 2, 3, 4. 1, 2, 3, 4. So that's that one. So I'm just reading the table in my head. I'll try my best to kind of talk you through this. The short form is the last noble gas, which is still helium. So helium, 2s2, 2p4. I'm going to come back to the box. Oh, I can do the boxes as well en route. So we've got, this is carbon, 2s2, and then there you go, 2p2. Notice in the last section, the electrons are going in. They're not going into pair first. Because there are orbitals on the same energy level, they'll fill up an empty orbital rather than a half-full orbital because they'll repel each other. The next one for oxygen, 1s2, 2s2, 2s1, 2p1, 2p2, 2p3, 2p4, and I'm done. There's oxygen. Next, fluorine is element number 9, 1s2, 2s2, 2p5, short form, helium, 2s2, 2p5, electronic boxes, 1, 2, 1, 2, 1, 1, 1, and then 2 goes back into pair. Next, starting to get larger now, magnesium's element number 12, 12 electrons, 12 protons, 12 electrons, so that's going to be 1s2. Back to the beginning, 2s2, skip over to the p block, 2p6, back to the beginning, 3s2, and I'm done with magnesium. Now we've got a new noble gas at this point. So magnesium's here. The previous noble gas was neon. So we've now got neon, and we've now got 3s2. It's box configuration 1, 2, 1, 2, 1, 1, 1, 2, 2, 2, 1, and 2, and we're done. They're slowly getting bigger. Sulfur, sulfur is element number 16, I believe. Element number 16. I'm gonna check that one. Don't do sulfur enough. So sulfur is element number 16, 16 electrons. 1s2, back to the beginning. 2s2, skip over to the p block. 2p6, back to the beginning. 3s2, skip over. 3p, now I'm going to count them. 1, 2, 3, 4, and I'm done. 3p4, still on the neon line, so neon, 3s2, 3p4. Box diagram, 1, 2, 1, 2, 1, 1, 1, 2, 2, 2, back in, and now we've got the 3p4, 1, 2, 3, and then 1 paired up. I like it. Right, potassium, element number 19, 19 electrons, 1s2, back to the beginning, 2s2, skip over to the p block, 2p6, back to the beginning, 3s2, skip to the p block, 3b6, and then 4s1. Now we've got a new noble gas. We're now at the argon because there's potassium's the previous noble gas. This now becomes argon. Yeah, so this becomes 4s2. Right, boxes, 19 electrons. 1, 2, 1, 2, 1, 1, 1, 2, 2, 2, 1, 2, 1, 1, 1, 2, 2, 2, and potassium, 1 electron in its outer shell. Like it. Cool. That looks like a full head, and it shouldn't be. It should be a half. It's 1 electron. Next, titanium, element number 22, I believe. 22 electrons. Let's just check that. Element number 22. Now, this one is the first one of any difficulty. Reminder that the D block, the entire D block is out of sync. Yeah, instead of this block here should all be up 1. Yeah, it should be up 1, but it's not. And the reason for this, of course, is because this is the 3D rather than the 4D. So let's run it on our homework. So 22 electrons, going to read it off. 1s2, hydrogen, helium, back to the beginning. 2s2, skip to the p block. 2p6, back to the beginning, drop a row. 3s2, skip over it. 3p6, back to the beginning. 4s2, and now we get the titanium of 3d2. Now, we'll check the previous noble gas. Titanium, the previous noble gas is argon. So we can do that. So this is still argon. And I'm going to have the 4s2, 3d2. Let's fill it in on the table. 1, 2, 1, 2, 1, 1, 1. Back to pair up. Yeah, then 1, 2, and then again 1 in, and then, by the way, it's called Hund's rule. Hund's rule said that 2 electrons cannot exist in the same, under the same spin. Sorry, Hund's rule was about spin. This is about minimizing repulsion. 1, 2, there's the 4s. Now we get the 2 electrons for titanium in the D. There we go. Now we're only going down to bromine, so only 5 more to go. Iron is element number 26. So we're going to start from the beginning. 1s2, 2s2, skip over, 2p6, back to the beginning. 3s2, skip over the gap, 3p6, back to the beginning, 4s2. Now we're out of sync. Yeah, we're into the 3D. We've just hit calcium, we're in the 3D. 1, 2, 3, 4, 5, 6. So this is the 3d6. Configuration is still argon, and that's 4s2, 3d6. Let's look at what that does now for the pictures. 1, 2. Gonna just skip across, then on to the next one. 1 in, 1 in, 1 in. Now they pair up. Yeah, and then 1 in, 1, and then again, same thing with iron. 1 in each one. Yeah, and then it goes into pair up. There's iron. Right, chromium. Right, guys, this is today's lesson. Chromium is special. Now, what you should have done is what is called, oh, hang on. So why is potassium argon 4s2? Sorry, shouldn't be. Apologies, 4s1. Thank you, Yihun. Yeah, because the last noble gas before potassium. No, it should be 4s1. He's absolutely right. Don't know what's happening now. No, I just made a mistake. Sorry. Yeah, thank you for the fixing. Chromium. Chromium's element number 25. Now, this one's important for today's lesson. What you're about to write down here, guys, is called the expected EC. Expected. Now, this is actually incorrect, and this is today's lesson. So 1s2, 2s2, 2p6, 3s2, skip 3p6, back to the beginning, 4s2, 3d4. that is what was expected. Oh, hang on a minute. 20, not 25, it's 24. There we go. So now we have argon, yeah, 4s2, 4s2, 3d4. This is the expected EC, and now this is actually really important. So I'm actually going to tick my first learning objective off today's lesson. The reason why chromium is odd is because this is what we expect. Now, what I'm going to do is I'm going to color code all these. Yeah, so let's go for green. Whoa, that's thick. Let's try shrinking that down a bit. There we go. And then back to red. So this is what was the expected EC. Now, this actually isn't the case. The reason being is chromium, this is your first note for your notes, guys. So today's lesson, by the way, the title is Electronic Configurations Part 2. First learning objective, know the oddities of the table, chromium and copper. Now, I've said etc. Now, the reason for this is because in reality, the oddities, so if I spot chromium and copper, yeah, the oddities are here and here. But in reality, it's actually everyone in these groups. Yeah, these guys are all strange. They all do something odd. And I'll make that note in our exercise books. So the first note for today. So let's do chromium first. Chromium. So its expected EC, electronic configuration, is 4s is previous noble gas, is argon, do the short form because that's all that matters. The expected EC is argon, 4s2, 3d4. But this isn't actually the case. Its expected EC is that, but changed by color, its real EC, its real electronic configuration is this, argon 4s1 3d5. Now, I'll tell you why. Now, what's happening here is the fact that if you remember my energy level diagram, here's the 1s, there's the 1s, then we have the 2s, then we had the 2p, and then we had the 3s, and then we had the 3p, and then we had the 3d with its 5 orbitals. That's the 3d, but the 4s, now what you'll notice is the 4s and 3d are very similar in energy. They're really close, guys. The difference in energy is rather small. Now, the 4s is lower, so it will fill up first. However, chromium has an opportunity. And look at the picture. Here's what chromium's was expected to be, was this. And what you can see is there is an orbital incredibly close to the 4s2. And what now happens is that you can get half full stability. One of the electrons in the 4s is promoted. One of the electrons in the 4s, I'm going to highlight it. One of the electrons, this electron here in the 4s, is promoted. And they do this because it's an empty orbital. There is an electron in this box here. There is electron-electron repulsion, meaning it doesn't really want to be in the same box with it. And there's an empty orbital really close to it with not much energy difference. So it promotes it. And it gains what is called half full stability. So the real EC is 4s1. I'm actually going to draw this as a box diagram as well. Yeah, 4s1. Here's the 3D. There you go. Didn't do that very well. Here's the 4s. I'm now going to fill this in red. So originally it looked like this. And then what's happened is one of the electrons has been promoted into that box there. And we've now got half full stability. It's because there's no more electron-electron repulsion in that orbital. Yeah, this is called half full stability. has half full stability. Electron from 4s, electron from 4s subshell moves to empty 3d orbital, reducing electron repulsion. It's more stable. So chromium, so guys, on your homework, you can make that fix for me now. So we go, chromium special. So that's not a 2 there, it becomes a 1. You can change your color for this. Yeah, so chromium goes to a 1 and then a 5. Same thing there, 1 and then a 5. And then over here, you can draw a little arrow, which hops it all the way over to there, like that. Just put a cross over it. There we go. It's cool, that. Right, next thing. Right, let's go to nickel. Nickel is not one of my oddities. Nickel is normal. Let's find nickel. Where are you, nickel? Nickel is there. Right, 1s2, 2s2, skip over, 2p6, back to the beginning, 3s2, skip over, 3p6, skip through, next, back to the beginning, 4s2, and then 1, 2, 3, 4, 5, 6, 7, 8, 3d8. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, back to the beginning, 4s2, 3d8. So we've still got argon, 4s2, 3d8. And that's got 28 electrons, I believe. Right, so boxes, you can see one, and then, so it all goes in, the 2 in, and then in, and then back to fill up in pairs, and then into here, and then nickel is as normal. It's got 8. So there, and there, and there, and we're done. Next, right, now we hit another specialty, another oddity of the world of copper. Right, so let's look at what copper's done. Okay, underline, this goes into your book notes as our lesson. So we've got copper. We're going to add a few more to this as well. So copper is element number 29, Cu29. It's got 29 electrons. Now, the electronic configuration that you guys did, which is the expected. Now, this question has been asked at A-level. They will simply say to you, write the expected electronic configuration of copper, followed by immediately, and now write the real configuration for copper. They love this. So this is 1s2. This is the expected electronic configuration. 1s2, 2s2, 2p6, back to the beginning, 3s2, skip the gap, 3p6, back to the beginning, 4s2, 3d9. That's the expected EC. Now look at the boxes. This is what copper now looks like. Yeah, so copper is in this scenario. Copper has all of these electrons. I need to put this in red. So this is what we expected. Yeah, here's copper. Right, now copper's got a different scenario because it still has electron-electron repulsion in the box here. However, there is a box right next door with another electron in it. Now, here's the thing. Now, you've got 2 choices. Copper has 2 choices, which is choice number 1. Choice 1 is to have a incomplete, messy, huge 3D and a full circular 4S, or choice number 2. Choice number 2 is a full huge 3D. Now, considering I've said messy, it is messy. Now, if you make a shell full, it becomes stabilized and a incomplete stable 4s. Now, what that's saying is, let's look at this just for an energy perspective. Yeah, so we can say, try and change my color here. Sorry. We can say unstable 3D and stable 4s. The stable 4s is stable because it's full, yeah, so an unstable 3D9 and a stable 4s2, or a stable 3D10 and a unstable but spherical 4s, which lends itself to stability energy anyway, stable-ish, yeah, 4s1. And what you realize is that it's either unstable and a stable small. It would just much prefer to have a stable huge 3D. So copper does the same thing. It promotes. So the actual EC, did I put real before? Yeah, real. I should have put actual, because that's how they term it in the exam. Actual EC of copper is 1s2, 2s2, skip to the next block, 2p6, back to the beginning, 3s2, 3p6, and 4s1, 3d10. So it's more stable. This is more stable since stabilizing messy, huge 3D. Yeah, they're stabilizing it. So copper and chromium are oddities. So you can make that change in your notes. So copper, the real one, you will have done the real, and then you can make the adaptation. Yeah, that's a 5, by the way. That's a 5. So the real one we can do in red. Copper is number 29. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9, expected. Argon, 4s2, 3d9, expected. Diagram, right, 2 in, 2 in, 1 in, 1 in, 1 in, back into pair up, 2 in, 1 in, 1 in, 1 in, back into pair up, 2 in, 1 in, 1 in, 1 in, 1 in, 1 in, back to pair up. So this was our expected. However, the real one, the actual electronic configuration, is that, and it gets crossed out. It leaves it. Let's call that stabilized 3D. And the last one, which is bromine. There we go. Should have gone to barium. Just should have done it. Should have gone the whole way. I'll give you more of these guys to practice. So bromine is element number 35. It's just not big enough for me. I just want to, size matters. 35. Yeah, we're going to go 1s2, back to the beginning, 2s2, skip to the p block, back to the beginning, 3s2, 3p6, 4s2, 3d10, and then straight into the 4, p, and 5 it is for 35. Still on argon, 4s2, 3d10, 4, p, 5. There we go. Sorry, it's not a 6, it is a 5. There we go. Right, 2 in, 1 in, 1 in, 1 in, back to pair up. 2 in, 1 in, 1 in, 1 in, back to pair up. Yeah, 1 in, 1 in, 2 in, 1 in, 1 in, 1 in, 1 in, 1 in, back to pair up. We're full. Now we go to bromine. 1 in, 1 in, 1 in, and we need to get to 5, and we're done. There we go. So out of those marks, it is 3 for each row. So 1 for that one, 1 for that one, and 1 for the boxes. So what I'm going to do is I'm going to go 3, 3, 3, 3, 3, 3, 3, 3, 3, 3. I don't know why I'm writing it down. I don't need to. Well, what I should have done is just count them. 5, 15, 12. 12 times 3 times 36. So the homework was out of 36. You can add this to our score sheet, please, folks. Here's our score sheet. You guys are 12E. It's out of 36. Electronic configuration. I will share this, guys, with you again if you need it. Let's give me a keyboard. Give me a keyboard. So EC, homework 1. We're going to get many of these. And it was out of 36. There we go. We can shrink that column. There we go. It's nice to see that Louis already on board, which is great. Thanks, Louis. Appreciate it. There we go. Cool. Amazing. Right. Okay, guys. So back to our lesson today. So what we've now done is we've now covered the... Now, I need to add this etc. in. So what we need to do is we now need to look at other people in those groups because they're going to do the same thing. Let's have a look at those groups. So I'm not going to go nuts here. And by the way, at A level, we stop at barium. Now, what that means is in chromium's column, it's only chromium and molybdenum that you're ever going to need to do. You're never going to go to tungsten. And with copper, it's just copper and silver. So what we need to do is, what I'm now going to ask you guys to do as a task is... Okay, you're now going to seriously impress me. Right, guys, what I'd like, please, is I would like, let's go for molybdenum first. Molybdenum, I believe. Oh, have I spelled that right? Molybdenum. I've got an extra E in there. Molybdenum, denim. There we go, molybdenum. So molybdenum, and what element number is this? This is element number 42. Right, guys, can you pause the video? I'd like you now to write out its actual. I don't want you to write down its expected, just the actual. Yeah? So we read it like a book. So I'm going to run the same thing again all the way through. And remember, this is the oddity group. Yeah? So let's find it. I want to get to him. So 1s2, yeah, 1s2, back to the beginning. 2s2, skip over, right? 2p6, back to the beginning. 3s2, skip over. 3p6, back to the beginning. 4s2, right? 3d10, we're out of sync. 3d10 into the 4p6. Sorry, yeah, 4p6, back to the beginning. 5s2. But it's wrong, isn't it? Because that should have been 4d4, but it's an oddity. It's promoted. Right. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, back to normal, 4p6, 5s1, 4d5. Promotion. Yeah, we've got promotion. Half full stability. There's molybdenum. Right, next, let's go for silver. Let's go for silver. Right, silver. Silver is element number 47. Yeah, so we've got 47. Let's read it off. It's in the same group as copper. You realize that it's just a case of reading the table. You just learn. You do not learn any shell numbers. You don't learn it. You learn to read my table. Yeah, 1s2. Back to the beginning. 2s2. Skip over. 2p6. Back to the beginning. 3s2. Skip to the 3p6. Back to the beginning. 4s2. Through the 3d10. Into the 4p6. Back to the beginning. Into 5s2. And then 4d9. But that isn't correct. Promotion. Right. 1s2. 2s2. 2p6. 3s2. 3p6. 4s2. 3d10. 4p6. By the way, I'm looking at it in my head. I'm literally imagining the table. I can't do this from my head. That'd be madness. And then 4d10 promotion. Yeah. Complete 4d. Yeah, stable 4D. You've got a big shell that's full rather than a full small shell. Yeah, I like it. Okay, so guys, on the chat, please, once you've had a go at it, give me a thumbs up if you got both molybdenum and silver correct. That would be wonderful. And of course, those are now in your notes, which is awesome. Right, learning objective number 2, ion configuration. Okay, so thumbs up. Thanks, Louis. Legend, good man. I'm really tempted just to show you, just for fun. Right, you guys stop at barium. I'm just for fun. I'm just going to show you tungsten just for entertainment value. Yeah, and before I do that, I'm just going to quickly do some clever things to aid me. Yeah, it's just nice to do it. So just for fun, you can also do gold as well. So if we were going to go to tungsten, now you stop at barium. You'll never have to do this. I'm doing this for fun. Yeah, shell number 1, 1s. Shell number 2, 2s, 2p. Shell number 3, 3s, 3p, 3d. Shell number 4, 4s, 4p, 4d, and 4f. The question is, where's the 4f? It's down here. This is the 4f. Cool. So let's run it. So I'm going to change my color. Right. 1s2, 2s2. If you want to have a try doing this yourselves, knock yourself out. 2p6, stretch and challenge, back to the beginning. 3s2, 3p6, 4s2, 3d10, 4p6, back to the beginning, 5s2, 4d10, 5p6, and then into the 6s2. Now, where's my next one? Why do we stop there? What's the star about? The star is I'm about to enter the 4f. This is now the 4f, 14. 4f, 14, and then back to the 5d4. 5d4. Now, what that now means is, because we actually look at that as a box diagram. Oh, my goodness me. Yeah. That's interesting. There's probably still going to be promotion. I want a box diagram. Where's my box diagram? Right. I kind of like it over here, to be fair. So if I just continue this, I'm just going to move this right in. Just going to see if we can actually figure out what it's going to be. Right. So I'm going to go back to green. This is actually quite interesting, isn't it, looking at this? So here's the 4s. Then we have the 4p. Yeah. Then we have, there's the 4p. Then we have the 4d. There's the 4d. Then we have the 4f, which has got 7 orbitals. 7 orbitals, 14 electrons. And then we have the 5s, which is here. 5s. That's the 4f. Yeah, 4f. And then the and then the 5s. Yeah. So what's now happened is we've now got a situation where in tungsten's scenario, where am I on my there I am. I should have written it all out. The 4f is full, but the s and the have I not gone far enough? I don't think I've gone far enough, have I? Haven't gone far enough. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 4p6, and then the 5s goes in. 5s2, then goes in the 4d. then goes in the 4D, so 4D10, then goes in the 4F. So then it becomes 4F14, 4F14, and then back to the 6. Hang on, then back to, is that right? I'm on the 5P6. I've gone and got myself lost just because I'm just not on the time. I don't usually do this. Oh, that's interesting. Where have I got up to? 5P6. We should be down at the 6S. Oh, I've made a mistake, haven't I? I haven't gone far enough. Guys, you should be ignoring me now. I've made the mistake because what should have happened here is the 4F haven't even been done yet, have they? Oh, this is why I shouldn't draw diagrams for these. Ignore me. I feel like I've scrapped that. I've gone and ruined it. Yeah, because the 5P6 is lower than the 4F14, and then that one, yeah, it then goes to the D and then back to the 6S before filling in that. We don't even fill this up for ages. Oh, the diagram's getting too long. I'm getting too messy. I'm just going to ignore it. Anyway, you do indeed get promotion. The 6S hops to the 5D. Yeah, it does actually do this. Yeah, and I can prove this. Check this out. Let's prove this. So hang on. Tungsten electronic configuration. Oh, look at that. No promotion. I don't believe it. I'm not entirely sure if I believe it. It suggests there's no promotion. I don't like it. Ooh. I don't even like how they've written it. This stupid internet's such a load of rubbish. Oh, is there no promotion? I thought there was promotion. Exception. Oh, there you go. The reason we get such fluid electron shuffle, two types of very close in energy. So it's saying that there's no kick up on tungsten. Huh? Ah, I tell a lie. Oh, okay. Ignore me then. Yeah, I stand corrected. Learn new things every day. Wow. No wonder they don't go any further than barium. Makes total sense. Right. Let's go back to iron. Let's go back to iron. Let's do ions. Right. Okay. So ion. Oof. Blimey. Am I like zoomed in? No, I'm not. I'm just on a fat pen. Okay. Ion configuration. That's really interesting. Tungsten doesn't do it. That means gold probably doesn't do it either. Okay. Ion configuration. So, rule, and there's only one rule. One rule. One rule to rule them all. See what I did there? One rule. When you remove electrons, they always come out from the last big number. Let me show you what I mean. Last big number. 4s2. Big number. Yeah, that there is the big number. So let's explain what this means. Okay. So what we're just going to use this rule, one rule, that's it. So we're going to just remove electrons from someone. Let's choose someone small. In fact, hang on a sec. No, let's start off with our transition metals because I need to get you guys used to getting bigger and bigger and bigger ECs. So let's choose someone. Let's choose. Oh, what a mess. Let's choose Rhodium. Why not? Hey, Rhodium, don't often see you. Let's run Rhodium. Blimey. Okay. Rhodium. RH. Is it RH? RU. I'm an idiot. Oh, that's Ruthenium, I think. Rhodium is RH. Ruthenium is RU. Sorry, I'll say someone else. So I'm doing Ruthenium, which is RU. Right. 1s2, 2s2, 2p6, back to the beginning, 3s2, skip over 3p6, back to the beginning, 4s2, 3d10. So where are we up to now? We're up to zinc. Keep going. 4p6, 5s2, and then is it an oddity? It's not an oddity. So it's 1, 2, 3, 4, 5, 6. So 4d6. I like it. So there's ruthenium. Now what we're going to do, we're going to ionize it. Ruthenium +1. The question is, I'm now going to remove, this says, remove 1 electron. Who do I remove it from? The last big number. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1, 4d6. The electron has come out from the last biggest number, which is the 5, not the 4. So in fact, the rule's wrong. When you remove electrons, they always, come on, Mr. Duncan, try writing some decent English. They always, whoa, okay, that's tiny. They always come out from the last biggest number. Yeah, the last biggest number. So you'd look for the big number and you look for the last biggest. Yeah, and you're like, who's the biggest? It's from the biggest big number. It comes from the biggest big number. Oh, I prefer that. Oh, I think that's amazing. Comes out from the biggest big number. Lol. So 4s2, big number. That's a big number. And you need the biggest, hence the 5s. Right, let's do ruthenium 2+. Yeah, so we're going to keep it all the same. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. It's all gone. 4d6. And we're done. It's completely vanished. That 5s is gone. So we've removed. So what would the next one be? Just for fun. Ruthenium 3+. Yeah, 3+. 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2, and 3d10, and 4p6. I'm sorry, I'm getting a little bit mad. And the last the biggest big number is that one. Now I'm taking it from that guy. So there is only one rule. Take the electron from the last biggest big number. Yeah, that's all. Now, just to explain to you why. The reason being is because when you remove electrons, what you're doing is you are, see that table's not correct, it's this one. What you notice is that you're moving, here's the nucleus. Yeah, and we're moving further out from the nucleus. And if you were to remove an electron, you're always going to remove the electron furthest from the nucleus, the one that's on the outside. If you heat up these elements, if you heat them or you ionize them, hit them with an electron, the electron you're gonna hit is the one on the outside. If you've got an element, if you've got an atom, which the nucleus is there, and then you've got these three-dimensional shells, underneath it, and these shells are covering each other up like this. Yeah, if you're gonna remove an electron, you're always gonna remove the one on the outside, which is the last biggest big number, because the shell number, the actual shell number, tells you the distance from the nucleus. It doesn't show whether or not it fills up correctly, but it tells you that it is further out. That is further from the nucleus, furthest out. Furthest, not furtherest. Oh, furthest out. So if it's the furthest out, if I'm going to remove an electron, that's what I'm going to be removing. Right, how are we doing for time? Doing really well. So Let's go to my learning objectives. My tablet's gone mad. There we go. So we can now do ion configurations as well. Now I want to write some ionization equations. So how do we actually do this? Now there's actually, so ionization equations. Now, ionization equations. Yeah, ionization equations. There's actually two types. There are two types of ionization. Two types of ionization. Now, can I just point out the two types in reality, it actually means two methods, but they give you slightly different equations. So method number one, I have already introduced you to. And method one is an electron gun. Yeah, so if we use an electron gun, this is mass spec device. Mass spec device. And those equations look like this. We put in element, let's put it element X, yeah, and it must be gaseous. I shoot it with a high energy electron, yeah, high energy electron from the electron gun. And what that does is it smashes into it, it knocks off an electron off my gaseous sample, and I have 2 electrons spat out the other side. Yeah, so this is method of ionization number 1. Now if you use an electron gun, it's quite difficult to remove successive. It's quite difficult to remove another, because once it becomes fully positive, the electrons then hunker down. They're attracted to the nucleus more, so it gets harder to remove. So we invented a second method. By the way, I think this method came first. I think method number 2 is to use heat. Yeah. So if you heat an element, and I mean you're going to have to heat the bejesus out of it. You're going to have to seriously heat this, guys. So if you heat this now, add just copious amounts of heat, it will vibrate faster and faster and faster and faster and faster, boom, and until an electron will fly off. Yeah. And that is ionization energy number 1. This is ionization energy number 1. The energy needed to remove 1 electron. This is ionization energy 1. And it's a really lovely experiment. This can be done. This was actually one of the first experiments done with electrons. They realized after, need to get my timeline correct. After J.J. Thomson discovered the electron, they realized that they could do this, that they could remove electrons one by one by simply heating their sample. So what you do is, it's a rather neat machine, actually. It's quite a nice experiment. What they do is they take a box and they put inside it a sample of X as a gas. So X goes in as a gas. By the way, it has to be a gas, because you can't remove an electron without, because if you put in a solid and you heat it up, it's going to turn into a liquid, then it's going to turn into a gas, and then you're going to lose the electron. So the energy would just go into melting it. So it would appear like your ionization energy was higher than it is. So you put in a sample of X, and then you heat the box. Now, they actually do this using microwaves. Yeah, they actually use a microwave generator, and they add in microwaves to heat this up. Now, by the way, just like your microwave does at home, and the particle heats up and up and up and up and up, and it gets hotter and hotter. Now, eventually, it's going to lose an electron. It's going to spit out an electron at some point. Now, here's the really neat bit. What they now do is they now make the box, the container that the gas is in, they make it the positive electrode in a current with an ammeter joined on. This is an ammeter. Now, ammeters measure the flow of electrons. Yeah. So the other, by the way, if anybody's interested, this is the positive electrode, yeah, and the other one goes to ground. If you're interested, the negative one just goes to ground. And what happens is that on the ammeter, I quite like drawing this dial, by the way. Yeah, on the ammeter, as they heat it up and up and up and up and up, suddenly an electron will fly off, and it'll hit the box. Now, when it hits the box, the electron hits the box and it flows down the positive wire, creating a flow of current, and you see a quick spike. Bing! So what in terms of so you do actually do temperature, yeah, so as they crank up the temperature, they're watching the current. Now what happens now is, as the temperature rises, they'll suddenly get a beep, they'll get a spike. And they go, oh, there's ionization energy number 1. And then it stops, it disappears, and the temperature continues to climb. Now, the great thing is, by the way, just to let you know that the samples, once you remove 1 electron to get the second one off, you need exponentially more energy. So, bing, you get another reading at a much higher temperature. And so you can steadily remove the electrons. And so this is your, and this is IE1. So what they now do is ask you question. They'll go, question number 2 is, or question number 1, because I haven't asked one yet. So write equation for ionization energy for aluminium, for Al. So very straightforward question. You're going to go, aluminium needs to be a gas, but we're removing the 4th electron. What that means is aluminium will become +4 at the end of it. This is the trap. Lots of people do the other way round. It means you start at +3 and end at +4. Lots of students make the mistake of going, oh, ionization of energy number 4, and they do that one. That is not ionization energy. This here is IE4. This one is IE5. Yeah, so just because they start at 4, it's a very basic trap. Yeah, IE4. Yeah, whereas ionization energy is actually starting at IE3, so just watch out for it. Yeah. You can even combine these, of course. So you can do another one, which simply states, so check my pen. Yeah, question number 2. Write the equation, we're at the end of the lesson. Write equation for IE2 and IE3 combined. Yeah, combined. Is that actually ED, isn't it? Combined. Is it like that? Combined. Yeah. So we now go, combined of, let's do sodium. Yeah. So, sodium. Sorry, sodium. Right, so we put in sodium gas. But hang on, I want to do ionization 2 and 3. So what that means is if I'm starting with 2, it must be sodium +1. I'm going to ionize it once to sodium +2 and ionize it again to ionize. So that's going to actually end up at sodium +3 is where I'm going to end up. Yeah, is that correct? So ionization number 2 would take us to this. Ionization number 3 would take me to that. Right, so now I can get rid of the middle ground because I'm combining them. And I'm going to have 2 electrons spat out on their side. So anyway, that brings me to the end of my lesson on electron configurations part 2. Oh, that's been a fun lesson. I hope it all makes sense. Enable device. Let's then go back to here. Wow, I learned something new today, guys. I learned that tungsten does not go through promotion. How amazing is that? I always love learning these things about the elements of the periodic table. It's cool. Right. Okay, guys, I'm going to leave you guys be. Have a great rest of your day. I'll post the homework on the classroom. You can actually finish off the worksheet I gave you, doing now the ions that are underneath. I'll see you guys all soon. See you later, guys.